So a student asked me a very good question. Why is a conservative vector field always the gradient field of some real valued function? Good question. Conservative vector field definition. A conservative vector field is often defined as a field that is the gradient of some real valued function, called its potential function. So it's defined that way. That is, a conservative vector field, f, equals the gradient of f. In 2D, it's the sum of the two partial derivatives with respect to x and y. In 3D, it's the three partial derivatives of f with respect to x, y, and z. Okay, I guess what I really meant to ask was, why is it that only conservative, aka gradient vector fields, are independent of path? Aha. Well, independence of path definition. The property that the work done in moving a particle between 2 points is independent of the path taken. Equivalently, if a particle travels in a closed loop, the net work done, the sum of the forces acting along the path multiplied by the displacement by a conservative force, is 0. In other words, if we go from point A to point A, the shortest path is just to stay there, and obviously the work would be 0. And if it's a conservative vector field, aka a gradient vector field, then no matter what path you take, if you start at A and meander around and then come back to A, the path is irrelevant, and therefore the work will still be 0. So what is actually being asked here is, if the work done by a vector field along a curve from point A to point B yields the same value regardless of whether the curve is a straight line segment from A to B or any curved path from A to B, why is it that the field is always a gradient, aka conservative field? In other words, why is the line integral f dot dr equal to f of b minus f of a for any curve from A to B if and only if there exists a potential function f such that the vector field's is equal to the gradient of f? So that's the question being asked. First, let's look at an example from real life. Gravity is a conservative vector field. There's somebody climbing straight up the cliff. I don't think I could do that. It feels like there's a lot of work being done on you, pulling you down by gravity, right? But it's going to be a shorter period of time. Whereas if you walk up a meandering path up that same mountain from point A to point B, it won't feel like as much work, but because it takes a longer time, it's going to end up being exactly the same amount of work. Whether we climb straight up a cliff or take a winding path up that same mountain, the total work done by gravity on us is the same. Therefore, gravity is a conservative vector field. Here's another example, different example. This time we're working against friction. And if we push a box around a room, if we go just a straight line from one side to the other, that's work. But if we take a meandering path and go up and down and back and forth and around for hours and hours and then end up at the other side of the room, obviously that's going to be a lot more work, right? So on the other hand, if you push a heavy box across a room, a straight line path will be less work than any winding route. So friction is not a conservative, aka gradient vector field. Now back to the question of why are conservative, aka gradient fields, and independent of path fields equivalent? Well, here comes a mathematical explanation. F is a gradient field if and only if it consists of the partial derivatives. Now we're going to do this in 2D, but the same thing holds in 3D. It's just easier to see if we do it in 2D. Now, given the line integral f dot dr, then we delineate those vectors, perform the dot product, and then parameterize f and r with parameter t. Now we have the integral from a to b, t goes from a to b, of the partial derivative of f with respect to x times dx dt plus the partial derivative of f with respect to y times dy dt. Now, that integrand should look familiar. What does that equal? It's the chain rule. df dt is equal to the partial of f with respect to x times dx dt plus the partial of f with respect to y times dy dt. Therefore, we can replace that whole kit and caboodle, the whole integrand, with df dt. And what will that give us? Well, that gives us a simple, one-dimensional integral like we had back in single variable calculus, and we can apply the fundamental theorem of calculus and evaluate the antiderivative of df dt, which would just be f at the endpoints, f of b minus f of a. Ta-da! Now let's look at a geometric example. If this is a gradient, aka conservative vector field, then if we go from A to B along that green line segment, the work done represented by all those little arrows will have a sum, and there are fewer arrows, sort of, than if we go along the blue winding path from A to B. There'll be more arrows, but the sum of all those, of all that, will be equivalent, because just because you have more doesn't mean the sum's not going to be the same. So anyway, there's a geometric example. Does that answer your question, young lady? Thank you. The fundamental theorem extends into many dimensions. If you know the endpoint, you can just do a simple subtraction.